Good day, everyone. This is the chapter 5 on the IPS. We are going to explore the industrial load monitoring and control system. And the outline for this chapter are first, we are going to explore the overview of the load monitoring systems. What are they, and what is the main function of the load monitoring system? And after that, we jump into the load voltage monitoring and control. This is specifically to look at the voltage control. And the third one, we are going to explore on the load frequency monitoring and controls. And after that, we will have some remedy on the frequency issues, that is using the load shadings method in the IPS. And this is the illustrations of the so-called the factory energy management solutions. Factory energy management solutions, and it is integrated with the server, or sometimes they use the cloud. Okay? So what this FEMS doing is it try to monitor the equipment and devices and the performance of the factory's outlets. Okay? So for example, in the factory we'll have the equipment and devices. We have a variety of the machines, motors, okay, including the chambers, and sometimes we use the robots based devices in as the equipments and devices. So we are going to monitor what is the performance of these equipments and the devices. And in the production line, for example, we'll have a series of the production lines equipments and the devices, including the fridge. Sometimes we have the fridge, we have the heater, we have the conveyor systems, and etc. So all these we are going to monitor the voltage, the frequency, and the currents as well. All in all, here we can monitor the power flow as well. Okay? So the power flow, for example, what is the power flow flowing at the section 1, for example. In section 2, what will be the Q, the reactive power flow. And of course, we are not only monitoring the basics of the electrical parameters, the voltage, current, frequency, the P and Q, but we also can monitor the power quality issue. For example, we have the harmonics, the voltage sags, voltage swell, and the flicker as well, using the FEMS. So same to the factory facilities other than the production line and the equipment devices. So we can monitor it at the distribution panel board, for example, to maintain the voltage level at the distribution panel boards, just in case we have some issue in the lighting, for example. And why we need to have the load monitoring system, or in a short we call it as a LMS in industry. So of course we will use the LMS to analyze our energy consumptions for the billing purpose, and we know how much is the cost that we are going to pay for the bill. Okay? So at the same time, we also monitor the power quality. The power quality issue is everywhere in the IPS, and it is very hard to mitigate it. Anyhow, we need to monitor the power quality. So how to monitor the power quality? Of course, we need some devices like the LMS to capture or to lock the data for a certain times or certain period of times. Then we try to diagnose through the history of the data logger that we obtains. Then we can understand the history of the power quality that we have. Then at the same time, the LMS also will interface with the energy management systems. Okay? So this is a load monitoring system. So load monitoring system is including mechanical and electrical parameters, but energy management system is only deal with the electrical system only. Electrical, for example, the voltage, the current, the frequency, and etc. But for the load monitoring, we not only focus on the electrical part but also mechanical part. For example, we try to look at the level of the liquids, for example. So that is the mechanical part. And of course, after we have these data, then we can easily control the flow of our energy, in all equipment and the devices. Why we need to have these all? Because at the end, for the future design and upgrades, so it's easy for us to upgrade. So because we have the database, we log all the data of the energy, the flow, the level, for example, into the data logger. Then we can retrieve the data from that data logger to check the history of, for example, the power quality issues and the problems that we have previously, and so that we can use this data to redesign our system to make it more efficient and effective in the future. And some of the benefits of load monitoring system, of course, we have a lot of the benefits to be gained through the load monitoring systems, and these are only the sums of the technical and the non-technical uh, benefits of the LMS. So for technical, of course, you can maintain the good power quality, and then we can minimize the fault risk, okay, because we always monitor our currents. Then we also can monitor, is there any faults happens, is there any maybe the precautions of faults happens. And sometimes we also can monitor the current. That means sometimes the current is fluctuating, that is due to the load changings, and our loads in the IPS also is changing all the time. And that's why it's very hard to maintain the especially the currents at the preset value. Okay, so preset value means whatever protective devices settings, so that is the preset value. So we try to maintain it within the preset value, so that we can avoid some unwanted accident, for example the overheated, that can give harm to our devices, especially the cables. Okay? With that, we can minimize the maintenance works and also prolong our equipment lifespans. Okay, for the non-technical benefits, of course, it will reduce the administrations, admins, and the maintenance costs. Better energy planning and management. You know where the power, the current flow, okay? And of course, finally, we will have the environmentally friendly systems. So before we can use the LMS, so we need to categorize our industrial electrical loads. So how to make these? So basically, we divided the industrial electrical loads into two categories. One is so-called non-interruptible loads, or we call it as critical loads. Okay? So these non-interruptible loads must be operated no matter it is blackout or not blackouts. Okay, because it is very important. So once we interrupt the process for the non-interruptible loads, so that means we will lose in terms of the cost, in terms of the productions yields, for example. Okay, so for example, just imagine the lighting. So when you have the production lines is operating, so suddenly the lighting off, so what will happen? Then you can imagine it, right? And same to the security cameras, for example. It's very, very important to have the CCTV switch on 24 hours. Okay? So that is about the non-interruptible loads. So another class or category of the industrial electrical load is the interruptible loads. Interruptible loads is a non-critical load, so we can switch on, switch off it temporarily, for a certain period of time. So that means it will not give any effect to the productions or the level of the comforts in our industrial power system. So the example is you just switch on your television, so it won't give any effects to your productions, for example. And what to be monitored in industrial power systems? So as I mentioned just now, we have basically mechanical parameters and electrical parameters to be monitored. So for mechanical parameters, of course, we can monitor the pressure. Okay, the pressure, for example, you use the gas related devices, gas related devices, then you need to always monitor for the pressure. And of course the flow, if you have the liquids, you have the natural gas, for example, so we need to always monitor the flow rates of these things in our industrial power system. So for electrical parameters, no doubt we need to monitor the performance. For example, okay, what is the status of our equipments at this moment? So we know that the equipment A is okay, equipment B it is not, maybe it is not in a good condition, for example. Okay, so all these we can monitor it using the temperature sensor, and sometimes the ventilation also, we can know the quality of our ventilation system in IPS. And another electrical parameters that we are going to monitor is the quality, the power quality. So know that we have so many power quality issues nowadays due to the advancements of the power electronics devices. Okay? So we'll have a lot of harmonics, a lot of voltage sags happens, especially during the contingency conditions, for example the faults. Okay? So we have a transient effect also. We have the transient effects, for example when we switch on and off of the power factor corrector, for example the capacitor bank, and etc. And of course we can avoid to monitor the basics of electrical parameter, for example in the P, Q, the voltage, current, and the frequency as well. One question is coming in is where can we monitor these all things? Okay, where should we put these LMS in our factory, for example? So normally the LMS is allocated in the main switchboard, because we are going to maintain the voltage, for example. Then we put a voltage controller or voltage monitoring system. Okay? And the distribution switchboard is more to the other productions lines, devices, the main devices, like for example the chamber, the heater, and etc., just to see the flow of the P and the Q, and at the main riser as well. Okay? So we have the sub distribution boards just to monitor a smaller load performance, for example. Okay, so what will be the power factor there? And of course we cannot avoid to monitor our MCC, motor control center. Okay? So MCC here you can monitor for the not only voltage and the currents, but the frequency is also very important, because the frequency were related to the timer, is related to the timer. So the timer is depends on the frequency operations. So if our frequency is deviated, then our timer that control the PLC, for example, also will be disturbed. Okay? And these are some of the one of the examples using the HMI, the human machine interface, and that controlling the PLC to monitor and control some of the devices. For example, they have the temperature controller, the pressure controller, so the timer, counter, and the tachometer for the speeds monitoring. And of course they have the motor driver, the DPM series. So this is a delta power monitoring series, power monitoring series. So it's under a Delta company. So the inventor, so this is the inventor, right? The interval, sorry. So this is the interval to look at the for example, if you have the UPS, then we can monitor our inverter. And you can see in the production line, for example, we have a series of the lines, the production line here. So from the plug-in processes, you have the spray. So we have the semi-manufacturing, testing, and bake as well. So we look at the some of the monitoring devices which is normally used in the IPS, industrial power system. So if you wanted to have the motor fault prevention solutions, then we can choose for the phase control relay. Okay, so this phase control relay will mainly dedicated to process integrating the three-phase motors. Okay, so it will monitor the phase sequence. So what is the phase sequence? RYB, for example. Okay, is it the sequence change or in the healthy condition or not? Okay, the loss of one or more phases. So sometimes the overload will happen at one specific phase, or it is due to the fault, internal faults in the winding. For example, it makes one of the phase loss. Okay, that means it's loss of the operation. That means for the three-phase motors, now the motor only operate at two phase only, and one phase loss. Then we can monitor using the phase control relay. So is there any unbalanced level between the phases? Then we also can use this relay. Same to the voltage level between the phases, or between the phases and the neutral. Okay, line to line or line to neutral voltage level. So if we wish to have the power supply fault prevention solution, then we can look at the voltage control relay. Okay, because the power supply is normally we need to control the voltage. Okay? At the power supply, we need to control the voltage. At the load supply, we need to control the currents. We need to monitor the currents. So for the power supply, the incoming power supply, that means the voltage control is very important. And we try to maintain the voltage level at the presets, at the preset level. So that's why we need to know what is the high and what is the low threshold for those preset values. And this voltage control relays will monitor, of course, phase voltage and line-to-line voltage, the peak and RMS value of the voltage, under voltage, and over voltage issues available in the IPS. So next is the load fault. As I told you just now, loads at the load level. So what our intention is to monitor and control the currents. It's not like the power supply, the incoming power supply. We are concerned more on the voltage quality. So at the load side, so the current will be our priority. So that's why at the load level we can use the current control relays to measure whether we have the under or the over currents issues. So it will continuously monitor the operation of electrical and mechanical loads. So these control relay are also applicable in field as varied as ventilations. You have the pump, the conveyor, for example. Okay? And for the network frequency, so now we're talking about the network frequency prevention solutions. So we can use the frequency control relays. Okay, so these frequency control relays will monitor the positive and the negative frequency variations. So that means the upper levels and the lower levels of the frequency variations. So for example, if we have 50 hertz, so the upper is plus minus plus 1%, and the negative side is the negative 1%. So that is the tolerance of the frequency. and we can monitor the either we have the over frequency or under frequency conditions. Okay? And in the filling or draining monitoring solutions, we can use the level control relays. So this is normally used for the liquids monitoring. Liquids monitoring, for example, you have the water tank, then you wanted to know what is the level of the water, and then you can use the level control relays. So level control is normally used a float switch. It's a float switch to control it. And for the pump management, so of course we can use the pump control relays. Okay, for this it can control either single phase or three phase pump. Okay, so we can monitor the digital control inputs and the monitoring of the currents. I mean the operation, the dry operation, and the overload protections for the pump. So for the operating rates monitoring solutions, then we can use, for example, we wanted to know the operation of our motors, okay, our motors or our machine. Then we can have the speed control relays just to maintains the certain motor speeds, okay, for example. So we know whether there is under speed or over speeds problems happens in our MCC especially. Okay. So for a temperature control solution, of course, the temperature control relays can be used. So it can control and monitor the temperature, temperature, especially in the pulley rooms, to check whether it remains within the regulated limit or not. Okay, now we jump into the load voltage monitoring and control, or in a short we call it as a LVMC. So LVMC is the load voltage monitoring monitoring and control. So it's normally used in the industry to consistently monitor the three-phase voltages of the motor circuit, okay, to avoid any harmful power conditions. So of course, talking about the voltage ratings, so it must be within the permissible limits, the plus minus 10%, for example. So the voltage levels in the IPS is much depends on the fluctuation of the reactive power, the Q. It's due to the motor loadings, because our motor loadings is always fluctuating. It's always fluctuating, and it is not fixed. It's not consistent all the way, but it is mostly fluctuating. It's fluctuating, and we know that the motor loading is draw a lot of the reactive current, or reactive power. So we need to have the Q compensations device to compensate it back, the voltage. Okay, these are some of the one of the illustrations for the LVMC. So we have the LVMC here. Then of course we can use the PT, but potential PT. This is the potential. This is the CT. Potential transformer. This is the current transformer. And the current transformer. Then we can know what is the existing currents and the voltage as well. Then it will go to the LVMC here to process it. Okay, so this LVMC will act like a voltage regulator, so that it will control the flow of the compensated Q into our loads, just to compensate back the voltage. So for example, if we have the feeder, and these feeder are serving a loads, so at the incomings terminal here, so we have the E. We have E. E is the voltage level at the incoming here, and the V here is the at the terminal load terminal voltage. So the voltage regulations is defined as the proportional change in voltage magnitude at the load bus. So this is the load bus, okay, due to the change in the load currents. So this is the load currents. Okay, say from no loads to full load, for example. Okay, so of course the loads power and the apparent power is equal to the PL plus JQL. Okay? So of course the voltage also much depends on the impedance, and much depends on the impedance at the feeders here. Okay, so this is the phasor diagrams. What it is illustrated is this is the current flow, the load current flow, which is lagging here. So you can see the power factor angle, the theta L here, and then we have the V is here at the load terminal, the voltage, and of course we have the loss, the power losses at the R, R of our loads according to the currents, load current, and as well as the reactive. The reactive part is the XL. XL. This is RL and this is XL. The voltage drop X at the R and the voltage drop at X. So we have the R and X voltage drops, and then it just form our E here. E is the at the incoming terminals. And talking about the voltage changes, so we can divide it into the vertical and horizontal. Okay, so this is the horizontal is due to the R, okay, R element, and this is the vertical is due to the X elements. Okay, so what is the V del VR and the J del Vx? We will see it next. So the voltage drops is defined, the VR. VR is the voltage regulation. So it is equal to the E minus V divided by V. Okay. So or E minus V is equal to the del V. Okay, del V divided by V. So without the compensation, so the source and the load currents are the same, and the voltage drops due to the feeder. We can use the IL to calculate it. Del V is equal to E minus V, or it is equal to the IL multiplied with the ZS. The ZS is the impedance at the feeder here. Okay? So XS is RS plus JXS. So the relationships between the load power and its voltage current is S, as you have learned in the power system. S is equal to the VI conjugate, VI conjugate here. Don't forget the conjugate here, and it is equal to the load power, the load power. So if we substitute the IL and the ZS, because previously we have the ZS, okay, is equal to the RS plus JX. Here we substitute into the del V, and del V is equal to the I. So this is the I, L, and this is the Z. Okay, so we substitute the ZS here and the IL here. Okay, so IL is taken from here. So IL is equal to the PL minus, because the conjugate we bring to here is become minus, and the PL minus JQ divided by the V. So this is the IL. Okay. And then we arrange it. We arrange it according to the real part and the imaginary parts. So that's why we will have the real parts voltage drop and the imaginary part voltage drop. So which is, this one is the horizontal and this one is the vertical. Right, from the previous equations we have the E del. Okay, so del is the angle, the angle variations, the angle difference between the E and V. Okay, so this is the del, and it is equal to the V, V plus the del V. V plus del V is equal to E. Okay, so this is V plus this is the del V, that means the voltage drop, and this is the voltage drop plus the V, it is equal to the E. and then we try to rearrange everything here. Okay? That means we rearrange, that means we just multiply with this one, and then we rearrange it so that we'll have the magnitude only. Okay, some seems like what we have in the power. So S is equal to the P plus JQ. Okay, so if we wanted to just to have the magnitude only, then our S become S square is equal to the P square and then plus Q square. So same to this one. So this one is seems like we have P and Q here. Yeah, P and Q, and this is our S now. So that's why it's E square, okay, is equal to the P square and the Q square. Okay. So that is the analogy to the power formula. Okay. And then after that we rearrange it so that we will have the V square as a title. Okay, V square as a title, and then you know that this is the in the quadratics. This is the quadratics equations. So V square now is our what is our title. Same like you have the x square. Okay? So x is our title. So now V square is our title. So that's why we have V square square. So that's why it's a V power of 4. Okay? And then we have the V here. Okay? Seems like we have the x square plus ax plus b, for example, here. Okay? So this is the x square plus the a, for example, this is ax square, ax, for example. So this is ax square, sorry, this is ax square plus bx plus c. Okay, so these are the c, and we have the a, of course a here is 1. Okay, so ax square. Okay, so that means x is v square now. Right, from there you can find very quickly the voltage. Okay? And of course if we wanted to make the voltage at the load terminal here equal to the E here at the incoming terminal, so that we need to use the compensator, the compensator, just to compensate back the Q, whatever Q lost here. Right, so that's why our E is equal to the V. So now we try to find how much Q that we need to have in our system so that we can correct our V to E. Okay, so this is the Qn. Qn is the net reactive power, the net reactive power at the load bus. Okay, now is the Qn is equal to Qc plus the QL. So QL is from the load, QC is the compensation, and the compensation Q. So from the previous equation that we have just now, E del is equal to the this one is the V plus del V. So this is all del V. So this is the V. Okay, so after the compensation, of course the compensation will inject the capacitive currents, and the capacitive current is always leading 90 degree from the reactive. Okay, so that's why it is leading 90 degree here. Okay, 90 degree. So this is just normal, and then with this one we can correct. You see the voltage, the V here is now equal to the E here, right? In terms of the vertical form. Okay, now we rearrange. Okay? So we rearrange the E square. Okay? So the E square. So like just now, we just take the magnitude. So the E square is equal to this one, and then now we rearrange it as a Qn. Qn as our title. Just now we arrange according to the V square. The V square was our title just now. So now we change. Even though we are dealing with the same formula, but now we rearrange it differently. Now we rearrange so that our Qn will be our title. So Qn is our X. So this is our A. So this is our B, and these all are the C. The C. so that you can substitute the B here, A here, and C here. Okay, so of course A is here. The value of A is this one. So B is this one. Okay, and C are these all. Yes, these all are the C. Right, so that you can find what is the QN, the QN. So the QN is the net, and don't forget the QN is the net. It is not the QC. Later on we need to have the QC after we found the QN, because we know the QL from the load. Okay, let's see the example here. So if we have one industrial feeder, okay, so the inductive load is 10 megawatts plus J 20 megawatts per phase, is having the incoming phase to neutral. Okay, phase to neutral. So the E is the phase voltage. It is not the line to line voltage, but rather it is the phase to neutral voltage. 6.35 kV. Okay, because we are trying to solve this problem using the phase, in the phase basis. So everything must be in the phase, not for the line to line, phase to phase. And the X over ratio of the feeder, okay, is 5. Okay, is 5. So with this X over ratio, we can find the impedance. Later on we can find the impedance. So the short circuit MVA for this feeder circuit is 200 MVA short circuit. Okay, so now we are required to obtain the terminal voltage V at the load bus. So what is the V? And B is if the terminal voltage V, we need to maintain as the incoming voltage E. So how much is the total compensation reactive power that we need to install? Okay, let's check the solutions. So of course, the first and foremost, we need to find the impedance. Okay, the impedance. So the ZS, okay, the impedance at the feeder circuits. So ZS is equal to E square over S. Seems like the V square over S. Okay, seems like you are finding for the base impedance, the base impedance. So E is the 6.35 kV, and then S is the short circuit capacity, 200 MVA. So per phase is 0.2. Okay, and then from the X over ratio we can find what is the theta. Okay, what is the theta for the SC? So the theta is 78.69 degree, so that we can simply find for the RS. RS is equal to Z, what we found here, Z in magnitude, and multiply with the cos theta, the cos theta, and X is the sine theta. Okay, so we know our R and X for S already. Okay, and after that we substitute in the very long equation just now. Okay, using the V square as our title just now. Okay, so we just substitute the parameter that we have. For example, the RS is this one. Okay, the PL is 10 megawatts. Okay, XL is this much, and the QL is 20 megavar. Okay, and this is the E. E square, and the V, of course we need to find what is the V later on. So the R, again the QL, so QL is 20, then PL is 10, is equal to 0. Okay, then we try to solve it, and we simplified it until we have this. Okay, we have this, and don't forget the V square is our title, so that we can use the quadrants and the quadrant formula to find what is the V. Okay? So because V square is our title, it seems like X, X. So V square is equal to the so this is the B minus B, minus B. So our B is the minus 31.62. So minus become plus, 31.62 plus minus. So this one is the B square minus 4AC, 4AC here, and divide by 2. Divide by 2. 2, I think 2A. Is A is 1 here. So that's why we have v square is equal to 30.96 or 0.66. Okay, so which one? So we have v square. Okay, then of course we can find a v, by just putting uh, the square root here, square root. So finally we have plus minus 5.56 or plus minus 0.81. So we need to understand that in the RMS value there is no negative. Okay, RMS value is always a positive, so that we can ignore the negative parts. And the maximum RMS value must be a feasible solution. So like just now we have 6.35 volts for E. Okay? So we can expect the voltage, the V must be a little bit lower than 6.35. So of course we can choose 5.56 as our solutions. It's more feasible rather than 0.81. Is too much voltage drop. Okay, for B, in order to find the net reactive power, we can see the formula here, and we use a very long equation just now. Okay, we just put in whatever it required here, but this times the Qn is our title. Qn is our title. So we try to simplify it until we have um, this one. We have this one. So we have A, B, and C here. So we substitute into the solution here, so that finally we'll have minus 2.27 or minus 386.5. Okay, by looking the figure, we know this is out already. Okay, so we don't choose for this one because it is not feasible. Okay, so the more feasible solution is minus 2.27. Okay, and then we know that Qn is equal to the Ql plus Qc. So we wanted to find what is the Qc. So the Qc is equal to the Qn minus Ql. So our Qn is minus 2.27, and then minus Ql is 20. So what we need to compensate the uh, the voltage loss and the voltage drops is we need additional minus 22.27 megavar as a compensator. Okay, then how after we monitor the loads, so just now was one of the method. We compensate the voltage using the injection of the Q, the injection of the Q. So the injection of the Q, we have several methods here. Okay, so the Q can be injected using the excitation control of the generator. So that means we control the voltage, by injecting the Q at the supply level. And this is at the power supply level, incoming level. And or we can use the shunt capacitor. A shunt capacitor is very famous because this is the capacitor bank, the capacitor bank or power factor corrector. Okay, this is at the load level. Okay, so normally we install at the load level. Same to this one, the synchronous condenser. It is at install normally at the load level also. Okay, so because we can optimize the voltage due to the load changes at the load bus there. So synchronous condenser, this is overexcited synchronous, overexcited synchronous machines, or synchronous motor. So another methods that we can use is the tap changing transformer. Of course, this is for the incoming, voltage control, the incoming. So that means we tap the voltage at the transformer sides. So for the excitation control of the generators, so normally they will have the generator. That means we control at the generator sides. So the generator will have the AVR, automatic voltage regulator. Okay, it seems like this one. So you have the exciter, and the exciter for the AVR. So the whole thing here is the AVR. You have the generator, so we can adjust the voltage according to the AVR here. So of course the AVR in this case is using the PID and through the exciter here and the rectifier. So the PMS is the power monitoring system. This is a power monitoring system. So we enter the to the ABS to control the generator through the exciter. So the shunt capacitor, so it is normally installed at the a load level and the loads bus. So normally if we have the a lot of the motor loading, so it draws inductive currents, so that it makes our power factor poorer. It's about 0.3 to 0.6 lagging, so that's why we need to compensate it back using the shunt capacitor. So at the same time, so we also can regulate back the voltage at the bus there. So using the synchronous condenser, so synchronous condenser, or sometimes we call it as a synchronous overexcited synchronous motor. Okay, overexcited synchronous motor is the synchronous condensers. Okay, overexcited. So when the synchronous motor is overexcited, that means you can twist, you can tune the power factor of the synchronous motor. If it's overexcited, okay, so that means it will deliver the reactive power. That means it will generate the reactive power rather than it consume the reactive power, okay? Because normally the synchronous motor or induction motor is consuming the reactive power, but for the synchronous motor we can adjust the exciter, okay? So that it become overexcited, then it will generate the Q. So the last one is the tap changing transformer. So normally as we have learned in chapter 2, so this tap changing transformer, we have either on load or off load tap changes. So on load is that meaning during the transformer is energized, then it will automatically adjust the tap, so to tap to a certain level of the voltage. And the off loads, of course, you have to de-energize the transformer first and let the transformer switch off, then you only can do the tapping. So it is very slow and it is ineffective. Of course, it is much cheaper than on load tap. So it depends on the turn ratio also. So the normal voltage control is you can adjust within the range plus 15% to minus 15%. So this is within the permissible voltage level plus minus 10%. Okay, that means you got extra 5% as compared to the standards. So I think this is all the content for the part 1 of the chapter 5, and thank you very much for your attention. So I'll see you again in chapter 5 part 2.